Check it out now, y'all.
NanoHub U, online instruction.
Welcome to tutorial 1.2, week 1. And as you know, the problem that I asked you to look at is to show that the difference between two Fermi functions, F1 and F2, which have two different electrochemical potentials, mu1 and mu2, that this difference can be expressed as in the form of this mu1 minus mu2 times this. Now, just for reference then, if you remember in the actual lectures, you see, when we obtained an expression for conductance, what I had done was, we obtained an expression for the current that looked like this, which was based on this basic idea that current flow depends on this difference between the two Fermi functions in the two contacts, F1 and F2. And we obtained this expression, and then we made use of what this homework asks you to prove. And at that time, I didn't quite want to take the time out to explain where that one came from, go through it, because what we're trying to do is get an expression for the conductance. But when you make use of that, what happens is you get a current that is proportional to mu1 minus mu2, and that's equal to the Q times the applied voltage. And so by making this approximation, you have a current that is proportional to the voltage, and so what's in between is like the conductance. So that's where we made use of this, and in future also in various contexts we'll be doing similar things. So it's important to get comfortable with it. So this is what we are trying to show. Now, as you know, this Fermi function, what it looks like is something like, let me write this here. Fermi function looks like 1 divided by exponential E minus mu over kT plus 1. Now, you'll see there is this two things appearing here. There's a E and there's a mu. So when I write F1, what I mean is, when I write F1E, what we mean is the Fermi function with mu equal to mu1. Similarly, when you write F2, it's a Fermi function with mu equal to mu2. So one way to think about it would be that this Fermi function, we think of it as a function of two variables, of E comma mu. It's a function of two variables. And when I write the difference between F1 and F2, what we are really writing is the difference between F of E comma mu1 minus F of E comma mu2. See? And so it's like at a fixed E, the mu is a little different, like mu1 and mu2, two different values. So what you can do then is, if you consider the partial derivative of f with respect to mu, so that's del f del mu. What that means is you hold E constant and you change mu. So as you know, that can be written as f of E comma mu1 minus f of E comma mu2, say two different values, divided by mu1 minus mu2. And this is an approximation, but it becomes exact as this difference tends to 0. That's like the definition of derivatives. So as this difference tends to 0, this becomes exact. But for small values, this is a approximation that you can use. And so what that means is, what we are looking at, this F1 minus F2, you could write as, that's this quantity, this quantity up here. So you could write that as del f del mu times mu1 minus mu2. So I could write this as so that then just follows from the definition of derivative and using this approximation. I mean, it would be exact if mu1 minus mu2 tended to 0, but for small differences, we could still use this. Okay. Now, the next point is, how do I show that this is equal to that? And of course, this derivative is taken at a value like the average of mu1 and mu2, and that's what we have put as the subscript 0. That is somewhere between mu1 and mu2. Now, the question is, how do I show that this derivative with respect to mu is the negative of the derivative with respect to e? So let me show that. So for that, let's go back to this function here, and let us say we give this quantity, e minus mu over kt, a name. We call it x. Then the general rule is that if I want the derivative of f with respect to e, or let's say, what I should be doing is, I could first take the derivative of f with respect to x, and then multiply it by the derivative of x with respect to e. On the other hand, if I'm trying to find the derivative of f with respect to mu, then I could take df dx and then take the derivative of x with respect to mu. So you'll notice this partial with respect to e and the partial with respect to mu, the first term looks the same, df dx. What is different is the second one. And since x is defined as e minus mu over kt, what you can see is the derivative of x with respect to e is 1 over kt, while the derivative of x with respect to mu is exactly the negative of that, minus 1 over kt. So one of these things then is exactly the negative of the other. So what that means is that derivative with respect to mu is the negative of what you get by taking the derivative with respect to e. So that then completes the proof in the sense that this quantity here can be replaced by the derivative with respect to partial derivative with respect to e. That's it.